Hello everyone. In continuation with the Thinking Machine series, I would like to introduce another point of view for building thinking machines. You should look at my earlier video series to get better context and continuity, which will help you get into learning groove. We are going to explore a frontier in artificial intelligence, the quest to build truly thinking machines. We won't be talking about simply making our current models bigger or faster. Instead, we'll delve into a paradigm shift inspired by the brain itself. We'll discuss how a brain-inspired computational framework, known as the Neuroidal model, can be equipped with the power of probabilistic reasoning to create a new generation of AI that can handle uncertainty, learn efficiently, and reason in a way that is recognizably intelligent. So, if current models aren't the full answer, where do we look for a better blueprint? We can look at the one working example of a thinking machine we have, the human brain. This isn't just another neural network. It's a theoretical framework designed to be cognitively plausible. It starts by respecting the brain's physical limitations, its finite number of neurons, their slow speed, and their noisy connections, and asks, how can a system with these constraints possibly achieve what the brain achieves? The focus shifts from pure performance to robust, efficient learning under realistic conditions. In the Neuroidal model, concepts are represented not by single units but by sparse sets of neuroids. Overlaps between these sets form the basis of association. This is biologically inspired, yet abstract enough to support symbolic reasoning and combinatorial learning. Now we have our blueprint, a powerful, flexible network of programmable neuroids. But there's still a crucial ingredient missing. A purely deterministic system is brittle. It can't handle the maybes of the real world. To achieve true intelligence, a system must be able to manage uncertainty. Probabilistic learning gives our neuroidal model the ability to manage uncertainty. Instead of storing only yes or no associations, it stores likelihoods, enabling nuanced reasoning, like saying, this is probably a dog, even with incomplete evidence. Our architecture begins with multimodal perception, converting sensory data into symbolic tokens. These tokens activate neuroid subsets, forming and strengthening connections probabilistically. An inference core retrieves concepts from partial cues. The neurosymbolic bridge handles reasoning, while a planner directs attention and learning priorities. The neuroidal model assumes a network that looks much more like the brain's cortex, a massive, sparse, random graph. Each neuroid is connected to a relatively small and random assortment of its peers. This web-like, recurrent structure allows for much more complex and flexible computational pathways than a rigid, feed-forward architecture, making it better suited for the unstructured nature of cognitive tasks. So how does the network learn? The goal of learning is to adjust the connections between neuroids so that the probability distribution represented by the network gets closer and closer to the true statistics of the world. This can be achieved through modified learning rules. For example, a probabilistic version of the classic Hebbian rule would strengthen connections between neuroids that co-occur as part of a statistically likely event. The challenge is to ensure these learning rules are local, meaning a neuroid only needs information from its immediate neighbors to update its connections. Researchers are showing how these simple, local adjustments can lead to the emergence of a coherent, global probabilistic model across the entire network. And finally, how does the system reason? This is where it gets really fascinating. The process of inference can be implemented by the network's own dynamics. Imagine you present a piece of evidence. This clamps or fixes the state of some neuroids. The rest of the network is then allowed to evolve according to its stochastic rules. Algorithms like Markov Chain Monte Carlo, or MCMC, provide a recipe for ensuring that the states the network explores over time correspond to samples from a correct posterior distribution. In essence, the network is performing a simulation, It's exploring a space of hypotheses and naturally spending more time on the explanations that are most probable, given both its prior knowledge and the new evidence. It's reasoning by running a structured, internal simulation of the world. It's important to be clear that this is a long-term research program. This isn't a product you can download today, but it represents a fundamental philosophical shift in AI, a move away from just fitting patterns in data towards building systems that construct and reason with their own internal, probabilistic models of the world. By synthesizing deep insights from neuroscience, theoretical computer science, and statistics, this approach provides one of the most promising and exciting paths we have toward a grand, ambitious, and ultimately achievable goal of building a true thinking machine. I am now happy to take any questions in comments. I will further share the more insights and details about how to build thinking machines and underlying principles in my coming video series. Please subscribe my channel and like the video so that I can bring interesting insights and updates on thinking machines.